Hello everyone, in this video we're going to go over section 2.2 class note problems. So first question, we have a couple properties or a couple sentences. We have P, it is sunny, and Q, I will go to the beach, and we want to write each of the following statement in symbolic form. We have, if it is sunny, then I will go to the beach. This is a classical P, then Q statement. Then if I go to the beach, then it's sunny. This is a Q implies P type of statement. If it's not sunny, then I will not go to the beach. This is not P, then not Q. I will go to the beach if and only if it is sunny. So this will be a P if and only if Q. Now for question number 2, we're going to do the opposite. We have the number is even as P, and Q will be the number is divisible by 2, and we want to write each of this statement in English. So we want to write P implies Q, and this will be if the number is even, if the number is even, then number is divisible by 2. Q implies P is the opposite, is if the number is divisible by 2, then the number is even. We have negation of P implies negation of Q will be the number is not even. Then, if the number is not even, then not divisible by 2. P equivalent to Q will be the number is even if and only if is divisible by 2. Notice that I'm shortening a little bit my sentences in there, but you can write completely the sentences if needed. Now for question number 3, we have a brief reminder of what the truth table for P implies Q is. So essentially, P implies Q is only going to be false when true is implying false. So in this case, this entry, and otherwise is always going to be true. Now we can use a truth table to showcase the property that we discussed, and is that P implies Q can also be equivalent to not P or Q. And we can set up a truth table. We're going to set up P and Q. So true, true, false, false, true, false, true, false. And then P implies Q, we just saw what it was, which is true, false, true, true. And then we need negation of P, which is false, false, true, true. And then negation of P or Q will be, I'm going to take these two together. So or, true or false, true, false or false, false, true or true, true, and false or true, true. Now, as you can see, both this and this, they have the same truth values in the column. So this means they're equivalent. They're logically equivalent. Okay, so that'll be the solution of this. Now for question number 5, we have the conditional statement, if n is divisible by 6, then n is divisible by 3. we want to write the contrapositive, the converse, the inverse, and the negation. Okay, so first let's go for the contrapositive. So the contrapositive, if this is a P implies Q situation, where let's gonna call this P, and let's gonna call this Q. So the contrapositive will be not Q implies not P. And so that will be if it's not divisible by 3, if n is not divisible by 3, then n is not divisible by 6. The converse will be if n is divisible by 3, then n is divisible by 6. Divisible by 6. And of course, this is a Q implies P type of argument. Now, the inverse will be if n is not divisible by 6, then it's not divisible by 3. Which is in a statement of the sort not P implies not Q. And of course, the negation of P implies Q is that we have P and we don't have Q. So we could say n divisible by 6, but not divisible by 3. Now let's go to question 6. This is similar. If it is Monday, then I have class. This is an implication, and then we have P, then Q. So the contrapositive will be negation of Q implies negation of P. If I don't have class, then it's not Monday. The converse will be if I have class, then it is Monday. Once again, this is a Q implies P. And now the inverse, there will be negation of P implies negation of Q. And so it will be if it's not Monday, then I don't have class. A little bit of liberty writing here, but this is how you will go about that. Now, let's use a truth table to show that P implies Q is equivalent to the contrapositive. So once again, PP, true, true, false, false, and then Q, true, false, true, false. The P implies Q. We should know that it's true, false, true, true. And then we're going to need the negations. So negation of P, negation of Q. And so false, false, true, true. And then false, true, false, true. And then we can check what is negation of Q implies negation of P, which we're going to see going in this direction from here to here. So false implies false, is true. True implies false will be false. False implies true is true, and true implies true is true. Now notice that P implies Q and minus Q implies negative P. They have the same values of truth in the column, so we can say that they're equivalent. So now let's build a table for the converse and inverse. So we start by P and Q, as usual. True, true, false, false, and then true, false, true, false. Then we have Q implies P. And Q implies P is going in this direction, so true implies true is true. False implies true is true. True implies false will be false. And false implies false will be true. Now, we need the negation of P, and we need the negation of Q. So the opposite to our original propositions. And now we want to do negation of P implies negation of Q. Notice that false implies false is true. False implies true is true. True implies false is false. And true implies true is true. The values, once again, are matching between the two things that we want to prove equivalent. So because the values match, they're logically equivalent. Now let's go to question 9 and 10. So for question number 9, we want to write the negation of each of these conditional statements. So if I study hard, then I will pass the exam. Since these are all conditionals, then I'm going to have the first thing and I'm going to negate the second. So I study hard and I will not pass the exam. That will be the negation of that implication. If the car starts and the battery is charged, I want to negate that. So I'm going to say the car starts and the battery is not charged. Here I have if x is bigger than 5, then x squared is bigger than 25. Then I'll say x is bigger than 5 and x squared is less or equals than 25, which will be the negation of this. Now, we can use logical equivalence to also prove that the negation of P implies Q is going to be P and not Q. So let's take a look at how to do that. First things is we're going to negate P implies Q. And then we know that for equivalence, this is negating negation of P or Q. We know that these two things are equivalent, right? P implies Q and negation of P or Q. We know that those things are equivalent, so we're doing the negation of this. And then we're going to apply De Morgan's law here. So negation of P. The negation of the or is an N. And then we have negation of Q. And then we have here negation of negation is P. So we get P and not Q, which is what we always say that is the negation of the implication. All right, let's continue with the exercise in the second video of 2.2.